let me ask you. Let's put it as an open question. Why will we do that? I mean, why not use steam and cooling water and instead go with two process fluids to exchange their heat? What do you think?
Save energy.
Save energy, right? So we need to save energy. Now here at this time, uh, we have to look at. I mean, how we can save or how much energy we can save. So we need to look into those aspects and how we can plan our overall plant layout such that uh, we can save energy to the fullest. I mean that's what probably we are um, heading to. So let me share my file here. So what we note here, you must agree that we had talked about these uh, energy consumptions. We have to save energy and recover heat from between process streams. So that is the objective here. So to do that, we have to understand few constraints within which we have to work here. So these are something like this. Suppose I have a stream which is hot stream available at 250 degrees centigrade, and the cold stream which is available at 110 degrees centigrade. And we can exchange the heat. So this process is known as heat integration. We are exchanging the heat of two process fluids. So one thing we note here is that the temperature will come down from 250 degrees centigrade to some value here, and this one is fed at 110 degrees centigrade, so it will be increased to some other value, and that value would be somewhere in between 58 and 250, and here it is 110 and 170. Now obviously you can see here that only by heat exchange we cannot reach to the place we are looking for. For example, if our coolant is available at 110 degrees centigrade, we can never reach 58 degrees centigrade. So we need to have a separate cooling utility as well. But at the same time, we can exchange some of the heats that is possible here. So some of the heat exchange we can use to our benefit. Now we need to plot this. We need to have this problem plotted as a function of temperature versus enthalpy. Temperature in degree centigrade and enthalpy in kilowatt. So we can write here the supply temperature is 250 degrees centigrade, which we are bringing down to 58 degrees centigrade. That is what we are doing, right? 250 degrees centigrade, we are bringing down to 58 degrees centigrade. And the other fluid is 110 to 170. So if we plot them on temperature versus enthalpy plot, that means as the temperature decreases, I mean enthalpy, you can write it as MCP and T minus T ref. Okay, so T minus T ref, so as the temperature decreases, its enthalpy decreases. So you can have a line like this, and if your CP is constant, so then MCP would be the slope of this line. So you will have these this temperature at supply it is 250 degrees centigrade, and here it is 58 degrees centigrade. So this is how the temperature would be coming down. This is the hot stream. And in the same way, the cold stream, it starts from 110, right? So it starts from 110 here. It starts from 110 here, and it goes all the way to 170. So this is the cold stream. That is what we have seen in our schematic drawing. So if we want to exchange the heat, if we want to exchange the heat, we can only do the exchange between these two locations, right? From here to here. And additionally, this part here to heat so to cool this beyond this point, we need the cooling utility So cooling utility for the hot stream, and heat and heating the fluid from this point to this point, we need the heating utilities for the cold stream. So these applies to this part of the line. So this part here, we can do the exchange. Here, this part of the heating can be done using steam, for example, and this part of the cooling can be done using the cooling water. So this phase. So this phase, the cooling can be done by cooling water. This phase of heating can be done by steam, and in between we can do the exchange of heat. Okay, so this is the temperature versus enthalpy plot. Now the fact is, why we are stopping here? We could have retained these. See, the enthalpy, it is T minus T ref, so the x-axis is flexible for us. So why we are stopping here, and why we are not sliding this line further this way? We can still maintain the temperature. The fact is that I have to maintain a temperature difference between these two lines, because I have to have the heat exchange from hot stream to the cold stream. If the difference comes down to 0 degree, definitely there will not be any heat exchange. The thumb rule here is at least 10 degree centigrade difference must be maintained. And in case you are using a special heat exchanger with fins, etc., or plate type heat exchangers, there you may still think of 5 degree centigrade difference, but otherwise 10 or more, this type of difference in temperature must be maintained. Otherwise, I cannot. Otherwise, what will happen? I mean, what will happen to the heat exchanger area? I mean, if I go to 2 degree centigrade difference, any thought? Yes.
Large area will be required.
Yeah, a large area will be required, so my capital cost will increase, right? So I have here, I have to balance between two things. One is the capital cost, another is the utility cost. So that is what we would be uh, balancing here. So now, so what we are doing here is plot both streams on temperature enthalpy axis. So y-axis is temperature, x-axis is enthalpy. For feasible heat exchange between the two streams, the hot streams must at all points be hotter than the cold streams. This is a major requirement. They must be hotter. Hotter by what amount? Hotter by at least 10 degrees centigrade. The region of overlap between the two streams determine the amount of heat recovery possible. So heat recovery, that means heat exchange from the other process fluid, that is possible. The part of cold or hot streams that extends beyond the start or end of the other stream cannot be heated or cooled by exchange of process streams. So hot and cold utilities are required. I think we have seen this, right? This part we need hot utility, that is steam, and for the other part we need cold utility, that is cooling water. One objective is to minimize the utility, referred as utility target. So one objective is we must minimize the utility. But in this regard, I mean, when we solve this problem, you will see that we will look into the both these capital costs. That means as we decrease this delta T, the temperature difference, the capital cost will increase because more heat transfer area is required. But we may save some money on the with the utility that you will see down the line. So what we will do is we will see that in fact this is what you would be doing in this assignment, is that you would be plotting uh, delta t mean. Mean is that extreme end where the minimum delta t that we are talking about 10 degree or so. So delta t mean. If I change delta t mean, we will see that the capital cost will decrease like this because heat transfer area will decrease. Okay, and we will see that the energy cost typically increases as we increase delta t mean. That we will show in a moment. And then our objective would be to find one objective would be to find out where is the minimum. Okay, so that gives me the minimum in terms of the cost. So one objective is to minimize the utility. So that can be one objective. The other objective would be to minimize the cost. I mean, where the minimum of the total cost. Total cost means the capital cost plus the energy cost. And obviously you can say that how do I get an annual estimate of capital cost? There are ways to do it. For example, when you purchase an say purchase a heat exchanger, so you are purchasing it today, definitely you will not go with the cash to purchase those. This you will study in probably later in later semesters. You will not purchase this with cash. What you will do is you will take loan, okay, and then purchase, and then you will not take a loan as such. I mean, maybe if it is for a big industry, you will probably issue some share, or through other means you raise money from public, okay. So you have to return the money, so that because public has a way to get their return from interest, okay. They keep it in savings bank and other places, so you have to give them more return, okay. So you lend some money, and then you have to pay interest, and let us say for next 10 years you will be using that equipment. So over 10 years you will repay the loan that you have taken along with the interest, because after 10 years you will assume that the book value of this equipment is zero. So you can now determine, now you can find out what would be the annual expenditure as far as acquisition of that capital equipment is concerned. So you can annualize that cost. And similarly, operating cost, how much of steam is condensing, so how much of steam is condensing, or rather we talked about enthalpy in megawatt, right? So you can see that we have enthalpy in, sorry, here we have in kilowatt. So we have an enthalpy in kilowatt. So this much of enthalpy delta H is to be provided by the steam. So many kilowatt, okay. And then that per kg of steam, what kind of kilojoule it provides, because if the steam condenses, it provides you the heat. So how much kilojoule you get from the steam, okay. And then if you run it for a year, obviously you have to leave out some shutdown period. So if you run it for a year, how much of steam you require, and then there is a price associated with it. Okay, I have some price for by US standard, and also I believe it is few rupees per kg, to say 2 rupees per kg. I mean, there are some numbers available for Indian context, so you have to get those numbers, and then you have to find out how much of energy cost that would be there to have your to provide this team for a year. So you have to generate these plots as a function of delta t mean, and find out where these minimum, where the cost mean total cost, where it is minimized. Okay, the other way of looking at it is you can also minimize the utility requirement. Okay, so that only the energy requirement is your primary m. You do not bother about the heat transfer area. You just assume some minimum delta T, and be happy with that. So this is the way we can handle this problem. So that is the way we are going to approach this problem. So in the plot, relative position of the two streams can be changed by moving them horizontally relative to each other. So I can show you how it works. You can see that if this is the way the heat transfer takes place, I have a supply, let us say that is same as the inlet temperature. So this is the heat exchange module. So here you have an inlet temperature, and here you have an outlet temperature. So this is how the hot stream is traveling from TH in to TH target, whereas the cold stream is supplied here, and we can assume this TC supply is equal to TC in, and this is getting cooled. So then we have, this was the plot that we have generated. Now we have removed those numbers. You can see this was the plot we had, and we already said that this part, for this part, we need cooling water. For this part, I need steam, and this part we can have a heat exchange. Okay, so TH in is equal to TH supply. So we assume that this is same. So it is entering here and it is leaving at TH out. Okay, so TH out is here, and then beyond that I need a cooling water or cooling utility which is reducing it further from TH out, that is temperature at this location, to TH target, which is temperature at this location. So this is how the hot stream will be treated. And the cold stream, in a very similar way, you have the supply which is same as TC in. So TC supply is TC in, and then you have TC out from the heat exchanger, and then you have this, you apply the steam, you are providing this heat. So you are providing QH amount of heat, so many kilowatt, I would say, because the x-axis is in kilowatt. So you have to provide that much of kilowatt there so that it can be heated to TC target. This is the value. So that's how we are working here. So we have a cooling requirement QC in kilowatt. We have a QH, which is the heating requirement in kilowatt. So this is the plot we have. Now I have a choice of shifting this line further. I have a choice of shifting this. So these numbers are given here. I mean, if you count from here, you can see this is 30 kilowatt and this is 40 kilowatt. So heating requirement QH is 40 kilowatt, and Q cooling requirement is 30 kilowatt. So this is something which we have by looking at the plot. Now you have a choice of moving this line, right? So this is the base case that we had worked with, and this was the heat exchange area, and this part was the heat this part we got, this heating part was accomplished by using the utility. It is a hot utility, and this part is the cold utility. This part is the cold utility. Now suppose I shift this line all the way there. I can theoretically, I can move this line all the way here so that the delta T becomes zero at this point. Of course, if delta T becomes zero, the area required would be infinite, but that is the theoretical limit, right? So if I shift it there, so what happens now? This was my original QC, right? When the base case was, this was the base case. So this was my original QC. Now you can see the QC is decreasing because I have shifted this line here. And since I have shifted this line here, the QH is also decreasing because earlier QH was this much. This was the earlier QH. This was the earlier QH. That was some 40 kilowatt or something. But then this is now the new uh, heating utility requirement because base case has been shifted to case 1. So you can see that as I decrease this delta T, then we can have reduced utility requirement, more efficient heat exchange, more efficient recovery of heat. Okay, not exchange, more efficient recovery of heat, but obviously at the cost of high surface area, because as the delta T decreases, the surface area required for heat exchange, that will increase. So you must agree at this time that if I shift, I would get a smaller delta T, and then smaller delta T means I will have smaller QH and smaller QC. Okay. Now this is the pinch point, because here this is the limit. You cannot go beyond this, because always the hot stream has to be hotter than the cold stream, right? So you cannot go, you cannot shift it beyond this location. So now you can work with somewhere in between. Case 1 is an extreme case, theoretical case, where you have shifted all the way delta T to be 0. This is the base case. You must settle somewhere in between. That means you can work with a delta T which is 15 degrees centigrade, let us say. So this becomes the pinch point. This is how we refer this as pinch point, and this would be the pinch point for the cold stream, and this is the pinch point for the hot stream. Okay, so the difference between the two pinch points would be then 15 degree, because you have chosen delta T mean to be 15 degree. You could have moved this line a little further and reduce this delta T mean to 10 degree. Then the pinch point would have come down a little bit for hot stream, and pinch point would have raised a little bit for the cold stream. Okay, so that is a possibility, but that way we could have reduced these QH and QC. And what we see here from this curve is that this reduction in QH and QC, that would be this delta QC, that is the reduction by shifting these from case 2 to case 1. Let us say if you shift from case 1 to case 2, you will see that if this is delta QC, this was case 1 is the theoretical case where delta T has been set to 0. Now if you shift by delta QC amount, okay, then you have maintained a delta T mean. This becomes the delta T mean, because all other delta T's that you are maintaining, these are all greater than this delta T. So this is the lowest delta T you have. So that is why I'm referring this as delta T mean. Now you can see the gradient here of this line is delta T mean by delta QC, and that same gradient will be maintained all through. And that same delta QC, that it would be same as the delta QC that you have accomplished here in the cooling so because QC was the QC case 1 and QC case 2, their difference is essentially delta QC. Now because of this shift to the right, you can show that the shift of this entire line will be horizontally everywhere. It is delta QC. So the delta QH, your original QH was 40 kilowatt or so we have been discussing, and then you can reduce it or increase it. You can see that this delta QH, because of the shift of line, that would be same as this delta QC. Okay, and that is defined by this delta QC is defined by the slope of this line and the delta T mean that you have chosen. Okay, so there is an intricate relation between how much saving you do in the hot utility side, how much saving you do in this cold utility side, and what is the slope of this line and what delta T mean you maintain. Okay, so this is how we are going to look at this problem. So now so what we note here is in the plot, relative position of the two streams can be changed by moving them horizontally relative to each other. So this part we have just seen. The lines will be linear if the heat capacity of the fluid, that is product of mass flow rate and specific heat capacity. See, what is the when we talk about this line, what is the slope of this line? The slope of this line would be MCP, right? Because this is y-axis is T and x-axis T, or rather should it be 1 by MCP? H is equal to MCP delta T, right? So your it would be 1 by MCP. So if you have generally this in our subsequent figures, we will just simply call it CP. P separately, not C subscript P, and that is the overall capacity of that fluid. So that is basically product of mass flow rate and specific heat capacity. Now, if you assume this product to be constant, why do you expect this product to vary? Because you're changing temperature, and heat capacity can be a function of temperature. Now, suppose you consider this specific heat to be constant within the temperature range that you are working here, then you can have a constant or a straight line with constant slope. But if the heat capacity is temperature dependent, then you have to approximate this line by a series of segments, and over that segment you can hold that heat capacity to be constant. So heat capacity, that they have to consider series of linear segments instead of a single line. So that needs to be considered to simulate non-linearity. So in case this non-linearity is significant, then one needs to look into this when it comes to temperature versus enthalpy plot. Now, if you so we have looked into these. Now let us look at how it works for a simple system. Suppose I have some numbers here. Uh, Let us say I have a cold stream and a hot stream. Supply temperature is available at 40 degrees centigrade, which is to be increased to 110, and hot stream is available at 160, that has to be reduced to 40. Okay, so the delta H involved in megawatt is equal to minus 12, and this is 14. Okay, minus 12 because it is temperature is decreasing from 160 to 40 here. So moment this information is available, you can find out what is so-called CP, okay, which is a product of mass and specific heat, mind it. So CP you can find out immediately by, for the two streams, by writing delta H divided by 110 minus 40, and here it would be 12 divided by 160 minus 40. So these numbers you can get immediately, the CP values. Okay, and you know that this CP value will give you the slope of these lines. So when we try to plot these, the hot stream is temperature is changing from 160 to 40, and the cold stream the temperature is changing from 40 to 110. So we have plotted them. Okay, and then we said that the you need the values of CP to plot this T versus H, so that those CP values are available from the from this information here. So you can generate these lines. You can consider them to be linear, and you can generate these lines. Now, suppose I maintain these delta T mean to be 10 degree. I mean, these are the two different cases that are shown. In one case, this delta T mean has been shifted. This stream has been shifted here from, so that delta T mean becomes 20 degree. And here the delta T mean is retained as 10 degree. Okay. So you have to manually place these lines. You have to draw these figure, and then draw these lines maintaining delta T mean. You have to draw these lines with delta T 20 degree, and then you have to find out what is QH mean in this case. That is basically this, what is this distance, or what is, how many megawatt you have here, and how many megawatt you have in this range. So in this range. Okay, so from the graph you can generate these values. You can see that this becomes, I mean, when you draw these, you yourself have to draw this, and then you have to figure out that this is 1 megawatt and this is 3 megawatt, and this difference is 11 megawatt. That is the heat exchange done. Whereas the moment you increase this delta T to 20 degree, you have to draw this curve yourself. You will see that this QH becomes 4 megawatt and this becomes 2 megawatt. So on both sides, there is plus 1 and plus 1. Here also plus 1 and here also plus 1. That is what we see, 2 megawatt and 4 megawatt. And you have the you recovered is decreased from 11 megawatt to 10 megawatt. So that 1 megawatt that you have added on both sides, that here we have a decrease in that recovery. So naturally you have more utility requirement in this case because you have recovered less heat. So you have more utility requirement in this case. And you on the other hand, since you are using a greater delta T mean, so this is the delta T mean here, this delta T is greater than delta T mean. This is the lowest value of delta T. So this delta T mean is 20 degrees centigrade. What that means is uh, you have less heat exchange area because you are working with a greater delta T. So this would work out something like this: 160 degree, and this is coming as 40 degree. So in this case, you exchange the heat, 11 megawatt you exchange between the two process streams, and then this stream from 50 to 40 you have to cool it down using cooling water, and this stream from 95 to 110 you are using steam. And here the steam requirement is 3 mw, and here it is 3 mw, and here it is 1 mw for the cooling water requirement, and 11 mw is the recovered heat. Whereas in this case the same, we have a very similar schematics, only the numbers change here. See, the numbers are changing here too. This is 95 degrees centigrade, and here it is 90 degrees centigrade, because this you will see from the plot that this has shifted, right? So earlier this line was meeting here. This was the temperature here. This level was where we are meeting. Now you have shifted. So it has come down from 95 to, so now it has come down, your cold stream, sorry, now it has come down, now it has come down from 95 degrees centigrade to 90 degrees centigrade. Okay. And similarly, the cooling water requirement, because of this shift, you can see it is 50 degrees centigrade here, and it is 60 degrees centigrade. So these sort of changes will happen if you shift this line horizontally. So you can increase delta T mean, but your utility requirements will increase and recovered heat will decrease. So this is the type of, when we look at the cost, we know that the capital cost will decrease with delta T mean, energy cost will increase, and the total cost, there will be some minimum, and that we have to indicate where this minimum lies. Okay, so we should be working with that delta T mean ideally. Okay. I mean, that is one way of looking at it. Now, if you are ready to, if you are ready to increase the capital cost, but your sole target is, I mean, that you can put appropriate weightage. How much weightage you put to the energy and how much weightage you want to put to the capital. There are ways to do this in optimization. So that needs to be looked into. If you do not have equal weightage to energy and the capital. Now, though the problem that is presented here looks all very straightforward, but it may not be that way. For example, here in this picture, I can see that this is one of the curve I have. This is one of the curve I have. So this is the hot stream coming down. This is the hot stream coming down, and this is the cold stream going up. And then I say that, okay, this part I cannot um, no, hot stream coming down, and in this is continuing. Suppose this is the hot stream. I have two different slopes. That means I have two different let us say MCP values. So this part I have the cooling water requirement, and this part I have the steam requirement for heating this cold stream. So this is something which we have looked into just now. Now, suppose we are working with suppose I have a situation where this is the plot and I have moved it here, and the end of the cold line, the line for cold stream, and the end of the line for hot stream, they are on the same vertical line, same value of H. So if this happens, then you do not require any steam utility, right? But you require cooling water utility, but you do not require any steam utility. If you move further down, if you move further down here, so in this case, you need a cooling water or cooling utility, and here also you need a cooling utility. See, heating utility is placed put here this way, and this is the cooling utility. So here you can see heating utility has been 0, and here I have, since I have moved even further, I have cooling utility in both these places. So if someone plots these QH and QC that we mentioned just now, you will find that the beyond this, I mean, if you continue to reduce delta T mean, suppose this is a situation which gives me a delta T mean, and if you even reduce this delta T mean further, you do not stand to gain anything. Okay, you do not stand to gain anything because your QC requirement remains unchanged. QC requirement on the left end is decreasing from here to here, but QC requirement is now coming up in the right end. Okay, so your total QC requirement it remains unchanged, and heating requirement is anyway 0. Okay, so these gives you a threshold value. This point where these delta t that we are looking at, or these value, this axis, or this, so these corresponds to a threshold delta t. Okay, now the same thing can happen with with the other end also. I mean, if you move, if it moves to the right, at one point you will see that the cold utility or cooling water cooling utility is not required anymore. You need only the heating utility, and if this line is shifted further, then you need heating utility on both sides. So this is again a very similar problem from the other side. So here also you will have, here if you reduce below this delta T mean, if you reduce the delta T mean further, you will have the QH mean is still required on both sides. You are reducing on this side, but coming up, you are reducing here. This is getting reduced to this, but you are developing another one here. So the total remains same. So essentially, you do not go below this delta T mean. So here you have a thresholding issue, that a threshold value of delta T is already in place, and you do not gain much by going, or do not much, you do not gain by going below this delta T value. So there is a threshold value that is there, and so that has to be checked. Okay, now so in this case, when you have a threshold, so at this, till this threshold, the energy cost will remain constant. Below this threshold, the energy cost will remain constant, and beyond this, the energy cost will continue to increase, and the capital cost, as I said, with delta T mean, it will decrease. But so the point is that this would be then considered the optimum. Okay, we do not too much. I mean, we don't have much scope of searching for an optimum below this, because it is not it is not possible. On the other hand, if your system is such that your optimum comes on the right side of delta T threshold, we can proceed with that. There is no problem. But this delta T threshold also is another issue that you need to look into. And then it is not just the delta T mean that gives you I mean, this will never be able to give you this value below this delta T threshold. I mean, delta T mean, if delta T mean is less than delta T threshold. So this aspect you need to remember. Okay. Now here comes a problem that we are going to uh, talk about in details. Okay. And probably a very similar problem I expect you to perform as well. So go through this problem carefully. Uh, your assignment would be a very similar problem. So now here in this case, you can see that there are two reactors, and you have a stream available, a feed available at 140 degrees centigrade, and then that is that has to be increased to 230 degrees centigrade. Then it goes to the reactor, comes out at 200 degrees centigrade, and the stream has to be, because you cannot leave this stream at 200 degrees centigrade, you reduce it to at least 80 degrees centigrade. So this is how it works. And the feed one has a reactor, it goes to the reactor. So it needs to be, the temperature has to be raised from 20 to 180 degrees centigrade. Then from the reactor, two streams go, one stream goes to the reactor two, which is to be, the stream comes out at 250 degrees centigrade, one goes to the reactor two, the other is cooled down to 40 degrees centigrade, and then it goes for a separation device where you can get an off gas at 40 degrees centigrade and the product at 40 degrees centigrade. So this is the overall schematics. Now you can note here that the delta H values are given. Delta H is 27 MW here. Uh, this is the, see, it is plus here and minus here, because here you are adding heat because you need to increase the temperature from 140 to 230. Here you are removing heat because you are decreasing the temperature from 200 to 80. The same thing here, you are adding heat so that temperature goes up from 20 to 180. Here you are reducing the temperature from 250 to 40. So that's why it's minus. And moment I get these values, if I assume that MCP is constant, I can find out, because moment I see, for example, in this case, I see 250 minus 40, that is the delta T. This is the delta H. So I can find out what is the MCP value. That we are calling it CP in our subsequent discussion. So this problem needs to be solved for different delta T means. And because first of all, this problem has to be solved such that the maximum amount of heat can be recovered from the individual streams, so that you do not, because you have delta H 27 MW, this has to be provide this here you have to add heat. So if you do not exchange heat, the only way you can do this is by using steam, as we have seen. I mean, you have to use a hot utility, and similarly you have to use the cold utility here to remove the heat. But instead of that, we need to use the available heat, or we have to exchange the process heat, exchange the heat that is available with the process fluid, so that we can minimize the use of QH and QC. So that's the idea. So you have to try this out for different delta T values and generate for which delta T value this is the cost is the total cost is minimum. Okay. Now I will revisit this because all the points are not clear in this question. So I will revisit this question again as I proceed. So I have now, you can see if I look at this schematic once again, I have a reactor one feed, reactor one product, reactor two feed, reactor two product. So I can separate these streams as cold stream, cold stream, and hot stream. Okay. So the way this thing works is, why I'm calling this a cold stream, because this stream is available at a colder available at 20, and I'm raising the temperature to 180. Whereas we call this hot stream because it is available at 250 and we are decreasing the temperature to 40. So these numbers and these delta H values are simply replicated here from this plot. So here we have uh, say, let us say I pick up we have delta H, four delta H values, right? Minus 30, minus 31.5, and plus 27 and plus 32. So those are the four streams I have: minus 31.5, minus 30, 32, and 27. So these are the delta H values I have. And so accordingly, I have the four streams where these delta one is here 140 to 230, that is the change. Here it is 200 to 80. Here it is 20 to 180. And here it is 250 to 40. So these are the changes in temperature. So that is exactly we are writing. Okay. Supply temperature, target temperature. And this is the delta H. These are the delta H values. So heat capacity. So this is we, as we said, it is CP the unit of it would be MW Kelvin inverse. Okay. Now Kelvin and degree centigrade, when we are talking about difference in temperature, so it is same. So we can work it interchangeably, because we are interested in when we arrive at this point 2, how we arrive at point 2. We simply write these as this as 32 divided by 180 minus 20. So that is how we get there as point 2, right? So 180 minus 20 is the difference between two temperatures. So whether that difference is in centigrade or Kelvin does not matter. So this is how we get these values. So all these values are tabulated: point 0.2, 0.15, 0.3, and 0.25. So this will determine what slope I will have for these curves. So these are the lines that are drawn. So you can see that what is the change of temperature from 250 to 40? That is one hot stream, and the other hot stream is 200 to 80, right? So 250 to 40 and 200 to 80. So these are the two hot streams. So these are the two hot streams I have. So this is how they are plotted. And corresponding delta H. See, here we are not writing here. We can probably break it here. The axis here, we can we can write it, we can make a small break here. So then it is, we are interested in this delta H. So this delta H is 31.5 and this delta H is 30. So they are covered here, and the corresponding CP values are given. Okay. So then we note here that first of all, when we look at the hot stream, I can see that between 80 and 200, I have a common portion, right? So if I use, see what we are heading to is something called a composite curve. Okay, this is called composite curve. So composite curve, it is a hypothetical line. Let me, I have written it somewhere, the exact statement. It is it is a hypothetical single stream that is equivalent to the individual streams in terms of temperature and enthalpy. So as if I, instead of having so many, instead of two streams, I will have only one stream, hypothetical stream. How can I come? I'm not mixing the streams. The mixing, your ethanol will remain ethanol, salt water will remain salt water. They are not going to mix, but their heat content will be mixed. So how, so that these are hypothetical lines. Okay. So you have the CP values given here. So I want to draw, when I draw this composite curve, I note that between 80 to 200, both these fluids are there, both these lines are there. And beyond 80, only this line exists. And beyond 200, also only this line exists. So that means the CP value here is 0.15. We know that between 200 and 250 the CP value will remain 0.15, and between 80 to 40 the CP value will remain 0.15, and in between I will have a combined effect of these two. So I can simply add the two MCP values. So 0.15 plus 0.25, so I get CP value as 0.4. So this is known as the composite curve as far as the hot stream is concerned. And we note here that when we try to draw this line, we have uh, this. This is uh, this is coming as 7.5, and this is coming as 6.0. Okay, and the overall range is 61.5, which is 31.5 and 30. That these are the two. This overall range is this, but when I combine them, this would be, the common portion will have 48 MW, and the individual portions, that means if I look at this delta H part and this delta H part, this delta H part and and this delta H part. So I can see that this is equal to 6, this is equal to 7.5, and this is equal to, the common portion is 48, total is 61.5. So this is how the composite curve for the hot stream will pan out. Similarly, for the cold stream, the temperature was increased from 20 to 180, and in other cold stream, temperature was increased from 140 to 230. That is exactly where we can see 20 to 180 and 140 to 230. Okay. So here also the same treatment has to be done. That is from 20 to 180. This is the line with CP value of 0.2, and this one with CP value of 0.3. So here also I have a common portion which is between 140 and 180. So this common portion is little shorter in this case. When we combine them, the common portion will have CP value, which is sum of these two, 0.3 and 0.2. So we can see the CP value as 0.5 for the common portion.
একটুখানি কথা বলি। আচ্ছা শুনুন,
Hold on,
যদি
hold on.
যদি ইউপিএস কিনতে হয় আমাদের, ধরুন আমার একটা অনলাইন ইউপিএস লাগবে, হ্যাঁ একটা ছিল সেই অনলাইন ইউপিএস একটা লাগবে, হ্যাঁ আমার একটা ওয়ার্ক স্টেশন আছে, তো সেটা আরও কিছু পিসি চালাবার জন্যে আমার একটা আমার এক
So this is how the CP is going to this is how the cooling composite curve for the cold stream will pan out. Okay, so you can find out these numbers 24, 15, and 20, and all these. So now we will put both the hot stream and cold stream, both the composite curves together. That's the idea. So this is the composite curve for the hot stream. I have three segments, right? We have three segments for the hot stream. This common part, I mean, where both streams are active, and this part. So this is the composite curve for the hot stream, and this is the composite curve for the cold stream, where this part is the longest. So then we put both of them together, both these curves together. So this is the composite curve for the hot stream, and this is the composite curve for the cold stream. And then you find out, then you move them. As we said, we need to slide them. We need to change the delta T mean. Here it is assumed 10 degree. You can go for 20 degree, 30 degree, 5 degree, and all these. And then you need to figure out what should be the value of this QC mean and QH mean. So this is an assignment which you have to perform, but for your case, the values will change. The values will not remain same. I mean, the original problem that we have, but more or less the schematic will remain same, and you have to draw these on a graph paper. I mean, I'm not probably talking about purchasing a graph paper and doing it using a pencil and eraser, but you have to draw it on Excel or some chatting software. So you have to draw these, and then see that when you maintain delta T mean, what is the QC mean, what is the QH mean, what is the total you get. So all these numbers have to be obtained by doing this hand calculation. And then we have, I have the series of sites available. A MATLAB code is in MATLAB. There are certain programs available which you can run in an interactive mode. And also I saw some students from IIT Kanpur, probably they have given a detailed MATLAB code. They have generated this code from scratch. They have written a MATLAB code where this temperature to generate these composite cars and pinch point, etc. So I have given that reference where the code is there. So you may like to go through the code and see how it is done. And finally you have to do one set of calculations. This is just probably 10% of the problem. Just 90% is still there. I'm going to discuss, but just to prepare you mentally what kind of assignment is going to come is you have to draw these physically by taking this all this data and then draw it on the ideally if you do it manually on a graph paper that is good, but you can use other spreadsheet and other places you can go, and then you have to employ those codes, either MATLAB or there are some codes available. I have those links, the codes written in Python where a similar work is done. So you have to know how to use those codes to generate these curves. Okay, so this is one of the main point that you have to address in your assignment. No, this is one of the points. Of course, the other points are coming. Okay, so that is what it is. Now, how do we? I mean, though we said that we will mix the streams and do this and that, but on a physical level, how it is accomplished. So you can see this is how we can look at it. See, this feed was available at 140 degree, right? 140 degree centigrade, and we have to raise this to 230 degrees centigrade before it goes to the reactor, right? So before it goes to the reactor, it has to go to 230 degrees centigrade. So you can see that this stream is, first of all, I have this stream already available at 200 degree and I have to bring it down to 80 degree. So this 200 degree stream is used here to deliver 12.5 megawatt of heat so that it can, and then it goes, so it goes through this heat exchanger, then it goes through another heat exchanger, and then it leaves as product 2 at 80 degrees centigrade here. And the other one here is the feed at 20 degrees centigrade. This is again getting heated to 52.5 degree. Then it is further heated to 140 degree. Then it is further heated to 180 degree. It goes to the reactor. And this heating is done by these streams here. One stream is providing the heat here. One stream is providing, this stream is available at 150. So this is providing the heat and cooling down to 106. And then further it is this 106 has to be reduced to 40. That is not possible with the process fluid. So here we use the cooling water and here we use the steam. Here we use the steam. So these are the two places. Otherwise you have the exchanges. Okay, so this is how the schematic drawing will pan out. So you can draw this diagram, a grid diagram like this, which is you have the stream, 4 streams we are talking about, 1, 2, 3, 4, and 4. So out of that, 2 and 4, they are being cooled. So they are available at 250 and 200 degrees centigrade and they are cooled to 40 and 80 respectively. And 1 and 3, they are heated. Out of that, 1 starts all the way from 20 degrees centigrade and to be heated to 180. Stream 3 starts from here, 140 degree, and goes all the way to 230 degree. And exchanges are made. I mean, the schematic drawing that I have shown above, those exchanges are made between these lines. You can see from here to here, I have 7 megawatt, 7 MW of amount of heat being exchanged here. And by this exchange, this here there is a reduction from 250 to 203, and here there is an increase from 181.7 to 205. Okay, that is the exchange. Then I have another exchange which is between this stream to this stream, and the delta H of this exchange is 8 MW, and the changes in temperature, you can see it is changing from 140 to 180 in this case, and in this case it is changing from 203 to 150. So this is the way you can draw the grid, and you can see from which stream to which stream heat is supplied and how much is the amount. Okay, and here once again you can see the cooling water requirement and steam requirement. These are given 7.5 and 10.0. So all these are consistent. So what I'm saying is this is the master curve, this is the composite curve, hot and cold composite curve. Okay, so and you have chosen a delta T mean, you could have made it 20°, all these values will change. Okay, so this is how it is going to look like. Now suppose now here in this case you would note that the pinch point is around 140°. I mean, if you look at this plot, it is coming to about around that range. I mean 140 or so. So in that range, the delta T, that the pinch point is. Okay. So pinch point, I have two pinch points, one for the hot stream, another for cold stream. And if the difference is delta T mean is 10 degrees, so then that means the difference in two pinch points would be 10 degrees. Now, one way to find out is that do the plotting in on a graph paper and see where all what all values you get, and then decide where the pinch lies. The other way of doing it is something called problem table algorithm, where you need to shift the curves. You can see that if I have the composite curve for the hot stream and composite curve for the cold stream, and their difference is in delta T mean, which is 10 degree. So what we can do possibly is that we can shift the composite curve for the hot stream down by 5 degree and lift the composite curve for the cold stream by another 5 degree. So then they will merge and the delta T will become 0. Okay, so what we can possibly do is we can change this, all the temperatures we can shift. Hot fluid reduce by 5 degree and cold fluid increase by 5 degree. If I do this, so this was my original problem that we have been talking about so far. Temperature, cold stream increasing from 20 to 180, hot stream going from 250 to 40, etc. Now I'm doing the modification here. I'm bringing in TS star and TT star, the two temperatures. So here you can see these are the cold stream. Both the temperatures are increased by 5 degrees. So 20 is increased to 25, 180 is increased to 185. Whereas for hot stream, they are reduced by 5 degrees. So 250 is becoming 245 and 40 is becoming 35. So, and the same thing applies here also. For cold stream, it is increased by 5 degree. For hot stream, it is decreased by 5 degree. Now, if we work with this modified temperatures and draw the temperature versus enthalpy plot and draw so we can expect that the delta T mean would be the two lines will simply merge, right? So now we work with this modified system. So you can see the temperature values given here. It is not 250. Okay, it is not 240, neither it is 20, it is 25 now. So all these temperatures are, cold temperatures are increased by 5 degree and hot are decreased by 5 degree. And then we write these values here. And then we note that overall I have these 4 streams, and 4 streams are running from what? Stream number 1, cold stream, which was going from 20 to 180. Now we have shifted to 25 to 185. Similarly, we have the other streams, the streams 2, 3, and 4. So it is not coming down from 250, rather it's coming down from 245 all the way to 40. not 35. So all these temperatures are shifted by 5 degrees. Hot stream decreased and cold stream increased. So now if we try to find out how it will work out here in this case is we will have the temperature, the interval temperature, we are calling it 245 to 35, those values, 250 minus 5, 240 minus 5. Okay. And these are the 4 streams that we are looking at with their corresponding CP values given. The stream populations are given. And then we note the interval delta T interval. So the delta T between these two values, 245 to 235, 235 to 195, and those differences are tabulated here in this case. Okay. And then what I do here is I find out sum of CPC minus CPH, CP cold stream, CP hot stream. Now here we have only 2 cold stream and 2 hot stream, and that is probably all 4 streams are available in this interval between 145 185. All 4 streams are there, right? So we have to sum up all the CP values of cold stream. So what are the cold streams? Cold streams are this stream, CP of 0.2 and CP of 0.3. So I will sum these two, 0.2 plus 0.3, that is 0.5, minus CP of hot stream. And CP of hot stream is, this is 0.15 and 0.25. So how much it is? It would be 0.4. So on here I have 0.5, here I have 0.4. So the difference is 0.1 plus 0.1. So you can see this is plus 0.1. So here I have all 4 streams. Here I have only one stream, and that happened to be the hot stream. So cold stream sum of CPC is 0, and sum of CPH is just one stream is there, and that CP value is 0.15. So since there is a minus sign, so I write it as minus 0.15. So this is how we do. And then what we do is now I try to find out what is the delta delta H internal, and to do that I simply multiply the delta T with the MCP value. Okay, so that I get the delta H value. So I multiply 10 with minus 0.15, I get minus 1.5. 40 with 0.15, I get 6. And then wherever there is a minus sign, I call this a surplus. Wherever there is a plus sign, I call this a deficit. And I compute this table. Next, what I do is I will visit this in a moment. So what I do is keep this plot. Next, what I do is I draw up this diagram where we are writing all the temperatures that I mentioned here. All the temperatures that I mentioned here, 245, 235, 195, like this. And then I write the corresponding delta H values here. So you can see 245 and then delta H minus 1.5. I get to 235, then delta H is 6.0, I go to 195, like this. So that is exactly, these are the y. 245 minus 1.5, 235, 6.0, 195. So that is how we have drawn this. So all these delta H values are listed. Now, if I start with 0 here, then this becomes 1.5. This becomes because we are accounting delta H of minus 1.5. So delta H of minus 1.5. So final minus initial, that is equal to minus 1.5. No, delta H is minus 1.5. So this becomes 1.5. So this becomes 1.5, and when I write 1.5 and 6, so this difference becomes minus 4.5. So what we are doing here is, so delta H is what? Let me see how alert you are. Delta H is this value minus this value, right? So this enthalpy minus this enthalpy, so that gives me delta H of 6.0. This value minus this value, that gives me delta H as minus 1.5. So I write the corresponding enthalpy values at treating these as zero. I write the corresponding enthalpy values for different intervals. And then we go all the way. We see that this is where the final 25 degrees centigrade, 25 degrees centigrade raised. So that is where we get to from hot utility to it is going there. So now you can see that the maximum negative maximum the lowest amount that I have is minus 7.5 mega MW. So now if I want to make all of these positive, the enthalpy, if I want to make all of this positive, so I have to add these 7.5 MW to every step, so that this delta H remains as it is, but this there would be no negative enthalpy value, because this, when this is 7.5 MW added, this becomes 0 MW. And the place where this 0 MW comes up, so that means there is no heat exchange at that time, at that place. So that 145 degrees centigrade will be considered the pinch point. So instead of drawing this plot, drawing this composite curve, one can so 145 means it would be, in one case it is 140, another case it is 150, so that the difference is 150 would be the hot side pinch point, and the cold side pinch point would be 140. So this is showing the average. So this is the pinch point. So you can come up with this pinch point even without considering the composite curve. So essentially what you have done is you have changed the temperature values. You know for sure that delta T mean is going to be 10 degree for you. Then you changed, you lowered the composite curve for the hot stream by 5 degree, and jacked up the composite curve for the cold stream by 5 degree, so that they meet at one point. And now you want to know where they meet, and you found that they meet at 145 degrees centigrade. So that is going to be the pinch point. So that is that. So you can do that without drawing the composite curve. So this entire exercise is done without doing the composite curve. So one can do this as well. This type of treatment is referred as uh, problem table cascade. Okay, so this is the problem table cascade you have to construct if you do not want to construct a composite curve. But your assignment would be to do both. That means you do the composite curve, and similarly and subsequently you do the this problem table cascade, and then match the values. You see that you'll get the same values. Okay, so that is the purpose. Next, what we do is next what we do is we try to find out uh, the area requirement for the heat exchange. Okay, in this case, so that we said that we have to do some analysis of the cost. Okay, so or we have to do some analysis of the capital cost and the energy cost. So at least we need to do this, and then if you just simply consider the total cost to be sum of these two, that is your choice. Or if you want to put additional weight to the utility, that is your choice. But first we have to find out what is the annualized cost for the heat exchange area that you require, and what is the annualized cost for the utility. So to find this out, you may note that since you are working with 145 as the um, pinch temperature, so you can note, or 140 and 150 as the two temperatures. So you can see these are the two streams that are the hot streams. One was available at 250 and the other was available at 200. And the third stream that was available is steam itself. That itself is a hot stream. STREAM. So steam itself is a hot stream. So these are the three streams you have, for these three streams you have for the as a hot fluid. And as a cold fluid, you have once again two streams here. One is 20 degree, another is one available at 140 degree, and you have the cooling water itself. So, so if 145 is the mean, if the two temperatures are 150 and 140, then you can draw an envelope and you can say this part is above pinch and this part is below pinch. Okay, so you can draw that. Now, if you try to draw a composite curve where see, one thing we need to note here is that though we have drawn this composite curve, there were changes in slope in many places. See, in this location I have a slope. In this location up to some point I have, so there would be change in slope in many different places, not just one. Okay, so depending on where all the changes in slope has taken place, either with the hot stream or the cold stream, one can produce segments and one can show. I mean, if you literally draw these, you will see that there would be 7 such segments possible. Okay, either there would be a change in slope in the hot stream or there is a change in slope in the cold stream. Okay, because of the mixing of the two CPs, right? In one temperature range, only one CP is valid. In another temperature range, two CPs are valid. In another range, this way it goes, and then finally you have the steam requirement and cooling water requirement, etc. So you can segment, you can provide, you can generate this kind of segments, and so it is 1, 2, 3, 4, 5, 6, 7. These are the segments, and the corresponding enthalpy values. These are drawn here. So one can note these for these segments, these 7 segments, one can generate plot something like this. I have a feeling that should we be uh, stopping for some time and then probably you please review this whole thing together, whole thing, and then probably we come back again at after some 5-10 minutes, because there is some more material to be covered. But I think at a stretch I have been talking for a long time. This may be strenuous for you.
That's a good idea. This is sure.
So let's I stop.
Yes, this is a good idea. I think let us have a break for 10 minutes.
Yeah, and during this time you can just recapitulate your thoughts, what all going on, and then probably we can and in reference to that we can again discuss the later part. Okay, so I'm just I'll stop sharing. Do I stop recording or recording should be on, Professor Mondol?
Let us keep it on. Let us
okay, let the recording be on. I'll be back in 7 minutes. Okay, thank you.
Hello, sir. Like regarding the shell and tube exchanger, so could you tell about the mechanical parameters? Like we are getting confused.
Yeah. So I think let us complete this this network problem, whatever Professor Ganguly has to demonstrate, and then we will talk about those clarifications. Okay.
Sure. Okay.
So let us start now. Okay. See, let me point out. You may say that, okay, where what would be the resources that I need to look into? Uh, what I'm going to post this part. There is a book which is available in the library. So since you have access to the library, central library, digital section of the central library. So you can, this is a book by Springer publisher. So you can look into this for the materials that we had talked about, this composite curve, etc. Because this book you should be able to uh, download officially from the central library site. And other than that, I have some of the materials that you need to, these are the resource materials that you need to look into. One is this paper. This paper, they have given the MATLAB code which they developed, some students from IIT Kanpur, they developed from scratch and they have given as an appendix to the paper. They were doing the same analysis, and they have written a MATLAB code where all this tuning is possible. And then I see that there are these in MathWorks file exchange section. These are available, and these will allow you to change things in an interactive manner. Okay, so it is not just writing code. You have to download something from that site, and then you have to feed that information in an interactive manner. Similarly, in GIT Hub, I see there are whole list of Python modules on pinch analysis available. So it would be your uh, responsibility to find a suitable code uh, to perform the analysis. That first you have to do all the analysis by hand manually. You have to do all these calculations, and then so at least that calculation has to be done for one delta t mean. I mean, choice of delta t mean can be 15 degree or 10 degree. That is your choice. You have to do all the calculations by hand, and then once you do this, then you can then you repeat the same exercise using one of these softwares to see that the values that you got, you're getting the same values from the code also. And then once you have that, then you repeat the uh, same exercise through software for various delta t means and generate these cost data, etc., and where the total cost is minimum, etc. So this is the book that you may refer, as I said, because you can not that this is the prescribed book, but this is available to you from Central Library website. And there are other books, but I do not know whether because that book is not those books are not available in the library, so I cannot I cannot I cannot specify them. Okay, I cannot say specifically that this is the book you follow. But the book that's book by Springer Publisher, that is good enough. I think at least to get the introduction on composite curves and pinch analysis, you get a fair idea. Now now we are continuing on that same problem. Now, when it comes to finding the cost, etc., there is one issue which we have not addressed so far. We said we sort of hand waved here that we need steam and cooling water, but steam at what temperature and cooling water at what temperature? So that those things need to be specified. So here you note that steam this is given to you that the steam is provided at 240 degrees centigrade and it will condense. So at the outlet you will have 239 degrees centigrade, and delta H it provides is 7.5 MW. Okay, so this is a new requirement that we are specifying. And for cooling water, it is available at 20 degrees centigrade and leaving at 30 degrees centigrade. You may say this is on a colder side. It should have been a little higher. However, let us take this as an example that okay, let it be 20 and 30. So these are the two temperatures, and corresponding delta H is given as 10 MW. So moment these two are available, so you can use these two temperatures to come up with some CP value. These were not available to you earlier. This is 7.5 and 10. These are already we have found from the composite curve, or we have already found from this analysis that we have discussed before. Okay, so if this is the delta H I have found, and these are the temperatures I assume, then correspondingly these would be the CP values. And the film heat transfer coefficient, or rather this is the heat transfer coefficient that we are going to use for calculation of the heat transfer area. So these numbers are given. Now we have to draw these. So again, we are going to that grid type diagram where you have the temperatures given. These are not, these are all exact temperatures we have. And now we note these are the hot stream temperatures, 250, 240, 239, all the way going to 40. and these are the cold stream temperatures, 20 all the way to 230. This is how it is. We had 7 segments, and if I start from 0 MW here, then for 7 segments, what are the corresponding MW we are writing? Because this would be the delta H would be 6. Here delta H is 6, like this. So these within this interval. So now we have, this is the steam. Steam has a CP value. Just now we said the steam has a CP value of 7.5. So we have written that, and the corresponding heat transfer coefficient that is given in the table, we have written it here. Similarly, the CP value for this other stream, the heat transfer coefficient, these are already we have worked with. These CPs, the heat transfer coefficients are new to us. Film heat transfer coefficient. Okay, mind it, it's film heat transfer coefficient. That is new to us. And then again, the cooling water here, it changes from 20 to 30 degrees centigrade. CP just now we calculated based on the delta H we have. And then we have the corresponding H value given. Okay, so with this understanding, what we do now is for each enthalpy interval, we calculate the LMTD. How we do this? Let me just complete these numbers here. This should be 1500. This should be 2650. This is 17.38, and this is 1875. This is of course 956. Okay. So how do we get this? We take this segment 1, 2, 3, 4, 5, 6, 7. So I take this segment, for example. In this segment, I have one hot stream with CP value 0.15 H, this that is coming down from 250 to 240, and one cold stream that is going from this segment. Cold stream temperature is here 225 to 230. So these are the temperature values. So I'm supposed to have a heat exchange between these two streams, right? This is steam. So I have a heat exchange between these two streams, right? So one 250 to 240, another is 235, 225 to 230. So you find out what is the LMTD. So that LMTD you are reporting here, delta T LMK for the first segment, first enthalpy interval. I have 7 such enthalpy intervals. So find out corresponding delta T log mean values. And then what you do is, why we need to evaluate this? For that you can see that area of the network. I mean, if I try to find out the area of network, heat exchanger network. So area of the network, total area, I mean area of heat exchange, I would say, that is equal to delta H divided by U into delta T log mean, right? So the total area would, so this is the area of the network for one segment. If I write it for one segment, this is the one segment. And this, then I have to write delta T Lm of kth segment. Now, if I do it for the total, so then total area, so that means then this side, if I write this as total, then we need to put it as total area is equal to delta HK, and then you have or in that case you will have a summation. This you would be, you can put outside, you can bring outside the summation k running from 1 to all the possible intervals, right? So k is running from 1 to 7. So that is what you need to look into. Now when u is constant, you can take this u outside, but when u is not same for all streams, where here I have age value for the films, right? That you have age values given. So in that case, what we will do is we will take all the hot streams that are available there, corresponding delta H divided by the corresponding H value, take the sum of these. Okay, so this is what we are doing is we are taking sum of all the hot streams. The delta H remains same for that segment. We already have that delta H value given there, and then divided by the corresponding heat transfer coefficient, film heat transfer coefficient. Okay, this is for one hot stream. Then we have for the other hot stream. So we need to sum them up for all the hot streams. And similarly, we need to sum them up for all the cold streams within that segment. So then total area, then if we try to write the expression for total area, the total area would be the total area if you have the u value varying everywhere. So total area would be sum of k is equal to 1 to, here in this case you have 7 intervals. For any other problem you may have 15 intervals. 1 by delta t lmk, which you have found out here for that segment, and for other segments you have to find out similarly. Sum of I number of hot streams, uh, qik divided by corresponding hi, plus another sum j for cold streams. How many number of, in some case you may not have hot stream, only cold stream. In some segment you have only cold stream, no hot stream. Or in some case you may have 4 such streams present, 2 hot stream, 2 cold stream. So then you have to sum them up, qik, and here it is qjk divided by hj. So hj is the film side heat transfer coefficient for the cold stream. So that means how we got this 1500 here? We get 1500 because we are talking about the first segment, right? So first segment you have what? H is this 0.0010. Okay, and Q is what? Q is, or the change in enthalpy is 69 and 67.5. So the difference is 1.5. So 1.5 is the Q divided by corresponding H, which is 0.001. And here again, I have 1.5 divided by 0.0008. So if you divide 1.5 by 0.001, you get 1500, and 1.5 divided by 0.0008, you get 1875. So these are the two numbers you get. So sum of hot stream, sum of cold stream for the first segment, you get delta T LMK you have calculated, because you know in that segment what is the hot stream in, hot stream out, cold stream in, cold stream out. So you find out delta T LMK, and then you write that area, that corresponding area is here 194.2. So this is only for k is equal to 1 segment. Similarly for k is equal to 2, because I have to do the sum. So sum means all the area, if I take the sum ak. So if I do that same exercise and then take the sum, I get this value. So that means this value is this total area. So total area what we are getting here is 7409.6 meter square. Okay. So this is how you would look into this is then this is the total area, because you are running this summation for k is equal to 1 to 7, 1 2 3 4 all the way to 7. So this is how you do this exercise and find out the total area. Once you find the total area, then you note down one thing, is that you have to find the annualized capital cost for the heat exchanger. So typically it is written first of all, if you leave out the interest part, if you just think of how the cost changes with the heat transfer area. Now it is common, you can write it as A plus B heat transfer area to the power C. This is how you can write the cost figure, where of course you need the value of A, B and C. And or there is a simplified way to write simply A plus B into area, that is treating C as one. Okay, so one can do that. Now I have some numbers available with me here. These numbers are in dollars. In US it is 40,000 US dollars plus 500 into area. Okay, so that means A plus B into area. You can have this kind of a form. Okay, so this is in dollars and area in meter square. So this is one way of doing it. The Now I was trying to find out how it would I mean what would be in Indian rupees, how these numbers would be, and I was in fact this would be your responsibility to do a thorough search and find it. For example, I just gave a search and immediately I see this one popped up, a paper where for double pipe heat exchanger this area versus total exchanger cost that is given, and you can see as the area increases then the cost is increasing. So you should have a better reference. I mean this is just a crude reference of how cost can be connected to area, but it is you should have a better reference and you should be able to find out what are the A and B values. Just for a quick comparison, you can see these are some of the figures in US dollars. Now so these you can find out as A plus B into area. Now, as I said, you have to borrow this money from someone and you have to return, right? So suppose you assume that you have rate of interest, the fractional interest rate per year. If you give I is equal to 10%, that means you give back 10% as interest. And if you choose the number of years as 5 years, that means within 5 years, you have to repay the entire loan and as with interest. So if you do that, then you have to find out, then whatever cost you have, then you have to multiply this cost with this I into 1 plus I to the power n divided by 1 plus I to the power n minus 1. Okay, this you can see this is available. I mean, in fact, this is a very standard you guys are taking other courses in, this is called Annuity Factor. So you can search this, and possibly you have studied this already in your financial or economics courses. So this is, so you have to multiply these I as 10%, so I becomes 0.1. So or instead of 10%, so I becomes, your I value is 0.1, and n is, let us say, 5 years. You can choose 10 years or other parameters one can choose. So whatever cost it comes to, that has to be multiplied by this. So that gives me the annualized uh, cost involved. So that within 5 years the entire loan will be paid back. So you don't have any more loan left. Now this is that is one thing. Now when it comes to this area, now this area, when you have these, this is the total area we have said. Now total area means all the heat exchangers that you have from stream 1 to stream 3, stream 5 to, so there are several heat exchangers we talked about, and this is the total area. Okay, so you have to find out what is the number of heat exchanger units required, and in this context, number of heat exchangers required, n, or number of units required. So if you multiply this by n, so this cost would be multiplied by n, but since area you are taking the total area, so this area has to be divided by n if you are multiplying the n to outside, or you multiply n to this 40,000 plus 500 into area. So that is a possibility. Now this n would be it is the way it is done is for simple cases. Basically, the book that I referred, you will find at the end there is a chapter on how to decide on n. There are some theorems available, but without doing much, I can think of how many streams I have above pinch and how many streams I have below pinch. So if I find out how many streams I have above pinch and how many streams I have below pinch, I see that I have 5 streams above pinch. If I put this dotted line as pinch, so I have steam, these 2 hot stream, these 2 cold stream. So I have 5 streams above pinch, and I have 4 streams below pinch, because this stream is starting from here. So this stream is not there in the below pinch. So below pinch I have cooling water, 1 cold stream and 2 hot stream. So I have 4 streams below pinch. So then this number of units is defined as S above pinch minus 1, number of streams above pinch minus 1, plus S below pinch minus 1. So this is how these numbers are obtained. So in this case, it would be 5 minus 1 plus 4 minus 1, which is equal to 7. So that n would be considered as 7. How to arrive at this expression? There was a discussion in the book at the end. You may refer it, and otherwise we will look at it if we can understand it any better. But this is how it is done. So now is this n is that 7. So when you multiply this 7, 40,000, I mean, if I go by US standard, so 40,000 plus 500 into this area 7409.6 divided by n. So that gives me in dollar the total cost of heat exchanger equipment, and that has to be multiplied by this factor I into 1 plus I whole n, I into 1 plus I whole n divided by 1 plus I to the power n minus 1. So that gives me the annualized cost. That means you will find that this comes to, let us say, 50,000. So these would be per year. If it is broken down into 5 years, it will not be 10,000. Rather, it would be 13,000 or 12,000, something more, because the interest has to be accounted. So this is as far as the capital cost is concerned. Similarly, you have to do the utility cost. So for utility cost, the US standards are, there are some numbers I can give you, which is 120,000 US dollars, 120,000. The unit would be dollars per MW and year. Okay, so MW per year. So that means this is for the steam, and for the cooling water, it is almost 1/10 of the steam's cost. So it would be 10,000 per MW per year. So this is the unit. So that means I have my utility requirement was what? In one case it was 7.5 MW, you remember, for the steam, and for cooling water it was 10 MW. So simply I have to multiply 7.5 and 10. So this into 7.5 and this into 10. So it will come to about, as I said, 10 times the total annualized utility cost. Steam cost would be 10 times the cooling water cost in this case. So this is so you can, on a per year basis, how much is the utility cost as far as steam and cooling water is concerned, one can get this. Now obviously you need to find out what is the Indian standard, how, and for that you have to do a very systematic search. Maybe the place to start is, you can see that how much rupees per kg the steam is sold. It is probably 2 rupees per kg, or there is some numbers which are there in it, and you have to do a systematic survey and find out what is reliable. Okay, so get the steam price of steam per kg and price of cooling water per kg. So you have to then calculate the mj per kg. That means that is sort of mj per kg means this kg of steam that you collect, your temperature is given. The temperature was given 240 degrees centigrade. So how much of heat is provided by the steam? So you get there, get this value. So per kg, how much it provides. So these, and similarly, how much per kg, because in cooling water, that water will evaporate, and that will give you some this mg. Of course, the cooling water has some other costs involved. Running, it is not just evaporation of water, because you have to purchase water, and there is a rate given for water also. Industrial water, when you purchase per 1,000 liters or per 1,000 kg, what is the cost involved? Some 10 rupees, 20 rupees, some numbers are there. So you have to find those from by Indian standard, what is the cost of that water. And then see, cooling involves evaporation of a part of water. So you lose that water. That water gets evaporated, and that's how you get the cooling effect. Okay, so how much of MW you require from how much of MW has to be removed by the cooling water? Okay, and how much of mj per kg a cooling water removes? This you get from the latent heat. Okay, so here you get an estimate of the amount of water required over a year, and then per year cost you will get. But obviously cooling water involves, other than mere water, you have to run the cooling water the fan and other utility lines. So this is not there some tuning also would be required on that. So please do a systematic search and come up with a better estimate of steam requirement in rupees per year and the cooling water requirement in rupees per year. So then you will get some idea of the fixed cost or the capital cost per year required, annualized capital cost required per year, annualized energy cost required per year. And then you make a comparison that, okay, I have chosen these values of delta T means, and these are my requirements. So now you tell me, now this is how it is panning out, and I would suggest this I would go by this delta T mean. So that is going to be the overall assignment. Now so the more or less the structure will remain as it is. Now I will change those delta H values, and for that I need to have a discussion with the other subject teachers that how we are going to operate, whether in groups or individually. So that I will discuss, and I'll put together this an assignment. And I have already given these references. So what I will do is, probably you figure out your other you complete your other problem on shell and tube heat exchanger. In the meantime, I will upload these I will upload this file so that you can refer this. But most importantly, you need those links in the at the end. That is very much required, because once you go through those, you will get many of these details cleared out. Okay, so I believe this is all I have as far as the introduction is concerned, and then as we proceed, we will look into it further. Professor Mondol, are you there?
Yes, I think
okay.
this is fine.
So they should start doing the ground preparation, and once shell and tube heat exchanger is over, they can start working on it. And so yeah, then Dr. Adak will take over, right?
Yes. So before we go forward with the drawing, is there any clarifications? I found somebody was asking some other questions related to the shell and tube exchanger. Shall we clarify those, or maybe yes?
Yes, sir.
Yes, so when we had this short 10 minutes break, there was someone who was asking some question on some mechanical components. I didn't, yes. So Shanmukh Shai Vardhan. Yes, Vardhan. Can you please tell us what was your question? No, he is not there. Okay, so in general, anybody has any issues regarding or any problems you are facing on the shell and tube exchanger as far as the calculation is concerned?
Excuse me, sir.
Yes.
Sir, I have make the word design less than 10%. So finally, should I consider the all the three criteria that are given, not just for a particular one, like?
Please say again. So you are getting the relative error in the overall heat transfer
No,
coefficient to
not,
be less.
not in overall, just in over design part, it is less than 10%. Then
Okay.
should I proceed in this one and write the final answer with this one, or to consider other two criteria that are from pressure drop and Reynolds number also? Pressure drop and U as removed.
What about the overall heat transfer coefficient?
Sir, I have sir, I have got error in 89% above in that part.
Yeah, so that has to be first satisfied. So see, it is sequential. First the overall heat transfer coefficient criteria has to be satisfied that it is less than 5%. If
Okay.
that satisfies, then you check for the pressure drop. If both of these satisfies, then you check for the over design factor. It's not one or the other. It's like I mean all of these.
Okay,
Okay.
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 Yeah, I got it.
Hello, sir.
Yes.
Hello, sir. Sir, like, will the design pressure be like the design pressure is 1.1 into the operating pressure. So our operating pressure will be the pressure that we got from the calculations, or will it be 15 psi?
So you choose your operating pressure. I don't think we have specified that operating pressure in the problem.
Yes, sir, it was not specified.
Yes, so you choose your
Yes,
operating
sir,
pressure. Yeah, so you can choose either 1 atmosphere or 2 atmosphere. That should be reasonable. Okay.
Okay, sir.
And sir, for like the gasket diameter, and sir, like for the allowable stress that we have to take from internet for the material we are using, or like we have to do something else. And for sir the gasket diameter also. And
So for the
sir,
gasket diameter, this would be equal to the internal diameter of the shell, isn't it?
but sir, if we are pressing it by flange, so like
So
if it is internal diameter of shell, then gasket, how we will place gasket? Like it will not be attached. That relates actually to flange actually.
yes. So what is the confusion?
About that gasket diameter only, sir.
So you want to calculate what should be the gasket diameter?
Yes, sir. Like I was reading that SI codes and all, but I was not getting anything.
So as far as I
Yes,
know
so
that
that
it should be equal to the internal diameter of the shell. But if you are considering the flange, then it should. Yeah, Professor Ganguly, please.
Yes, this we covered in our previous semester, right? You know how the gasket ID and OD is calculated. If see everywhere wherever the IS code says something, you have to follow. If IS code does not specify anything, you go by whatever is the IS code for general pressure vessels. So that is given in BC Bhattacharya's book. So you simply follow that procedure, isn't it? We had a gasket design assignment, right?
Yes, sir.
There the DO and DI was calculated, isn't it? There was a procedure to calculate DO and DI. So that
Yes,
same treatment for pressure vessel that will govern. I mean, unless if IS code for heat exchangers specifically stipulates any other requirement for gasket DO and DI.
Okay, sir.
Hello, sir.
Yes.
Sir, in case of tube sheet, for calculation of tube sheet thickness by shear, so there we need to calculate the equivalent diameter of tube center limit perimeter like that you said. So in that, to get perimeter, we need to join the holes of outer outscript holes. So how we can get that area?
What do you
I mean,
mean?
area we can get, but how we can get the perimeter?
Why not? So you calculate the total distance that is covered by calculating that you joining the points. That you have to do manually, right? After you choose a layout arrangement for your pipes in the tube sheet.
Okay, so
So like we have square pitch square arrangement.
No, it is nothing to do with the pitch. After you make the, I mean, after you create that layout arrangement, that you have to draw in a paper. There is no formula for that. That you have to draw in a paper, and then you have to calculate the total individually how much. I mean, how much are the lengths that you are getting by connecting these 2 points on that this thing will give you the perimeter between two center points.
Sir, actually, I am getting 52. The number of tubes is 52. So drawing the 52 tubes on paper and getting the perimeter is little tedious job.
Little?
Tedious job. I mean, I have to
Then
be perfect on pitch and drawing the on paper and
yeah,
then
so
joining the
see, there is
outstretch.
something known as a see how do you arrange the how do you arrange the triangular this tube sheet layout. So let me show you one type of sheet. These are generally available for the square arrangement. Generally, you can use the square plots or the square graph sheets. But for this sort of triangular pitch arrangements, you can use those triangular graph points, triangular graph scale. Let me see if I have one of those sheets, and that can be used to locate the circles in that sheet for the tube sheet layout. Just give me a minute. Let me find out if I have those sort of sheets. Check it here. There are sort of these graph sheets, very much like the triangular plots. Just give me a second. Yes, so I think that day only I showed you. Uh, So Professor Ganguly, do you happen to have these sort of triangular sheets where the students used to draw and mark the circles for the tube sheet layout?
No, I don't have, but it's not available in net, right? We
Maybe I'm
can
not
download.
using the correct keywords.
Okay, let me try also parallel.
Yeah, something like this probably. No, this is not the actual thing that I wanted to show. So something of this plot. So if you draw your tube sheet on a triangular graph sheet, these triangular pitch arrangements is already there. So possibly these points on these graph sheets can act as the center points to your tubes. So these sort of graph sheets are available for different spacings. And this could be used for your triangular arrangement. So you have to draw your circle essentially over this triangular graph sheet. Similarly, the normal graph sheets can also be used to draw for circular rectangular pitch arrangements or square pitch arrangements, or you can also prepare your own lines with the vertical sort of square grids. So this is how generally it is best or easier to arrange your tube holes in the tube sheets. Also, there are few online programs that helps you to allocate or optimize your tube layout area with the proper positioning of these tubes in the tube sheet, so that you maximize the available space with the tube sheet. right? There are some online codes or programs available where if you give the size diameter and if you give the number of tubes and you tell them the pitch arrangement as well as the pitch length, then it can give you the optimized layout of the pipe holes in that given diameter of the tube sheet. Okay, but this has to be done. I mean, I recall we used to provide these triangular graph sheets to the students in previous classes also, and people used to fit in like almost I recall 192 tube sheets also, up to 180 tube sheets also people did fit it manually. So this has to be done. You can of course make some approximations while calculating the perimeter, right, of that connecting the most exterior tube points, that you can do some approximation, you can ignore some and get at least more or less a reasonable estimate. But these tubes has to be placed for all the tubes in your tube sheet. That has to be done. Okay, Rushi Girish.
Yes, sir.
Okay. Any other question from anyone?
So just one more request. So like for the PDF you have provided for the IS codes, like
Yes.
how to calculate like the thickness of the shell from that, sir? If you could give an example, so like it would be very
No, but
helpful.
thickness of the shell is the normal calculation. You do it for your pressure vessels. That was taught to you in last semester.
Okay, sir.
Okay. That's the same way. Okay, then, so if I suggest that we now proceed with a drawing illustration for this particularly for this problem, and it is advisable that all of you try to do it parallelly in your own desktop computers also, so that you can also solve this out as it is illustrated in the class. Please note that in the next week class you have to submit, complete submission of this assignment has to be done. I request Dr. Jana to make a note of this and put the assignment deadline for next week's class. Right, so this has to be done by next week, and because you will be starting to work on the heat exchanger network problem by then. Okay, so please get all your doubts and everything clarified in today's class itself.
So next Tuesday till midnight.
No, next Tuesday before we start the next Tuesday's class, because today is the last class for this heat exchanger. From next Tuesday, they will focus completely on the network problem.
Okay.
Okay, so Dr. Nitai can proceed with the drawing illustration of this problem.
Yes, sir.
Please continue.
Okay, so I was told that if you have any problem of modeling any mechanical parts of a cell and tube heat exchanger, so have you tried it? Hello, is it audible to you?
Yes,
Yes, sir, it is audible.
So have you tried to make a model of a cell and tube heat exchanger? Anyone?
So has anyone tried with the SolidWorks drawing based on your calculations of the different components?
So we were not like able to calculate all the mechanical parameters.
Okay, so whatever, at least you got the shell diameter, right? So did you try to create a cylindrical cell in SolidWorks with some tubes?
Yes, sir, that is like tubes arrangement, but that was like I was confused in which type of arrangement. So like that is linear arrangement is done, that I have done, and for shell it is done, but not further than that, like not
So
the.
can you share your screen and show us what you have done in SolidWorks?
So that I have not saved actually.
Anybody else would like to share your work on regarding SolidWorks that you have done? No? Okay. Yeah, Dr. Meeta, I think let us proceed trying to show them.
Sir, the one thing is that there are lots of part, means the cell, tube arrangement, then the gaskets or the tube seats, and also the buffels, and also
Yes.
the cylindrical or the end part of this cell.
Yes.
So it will take long time to
Yeah,
make
yeah.
a
So we
complete
will
design
show
of
them.
the whole heat exchanger. But I
No,
thought that
I
students.
think in the last class you have shown them how to connect the tubes to the tube sheet, how
With
to
buffels.
arrange the tubes in a shell. So I think today you can focus more on the end parts and the head designs and all.
Okay,
Flange,
that's fine.
gaskets, those portions, right?
So okay, so today I'll show only you the cell and as well as the end portion of the
Yes, yes.
pressure vessels or cell.
End connections and all you try to show.
Okay, that's better.
Okay.
So let's take a new parts. So at first we have to take a plane for design a mechanical component. So I'm taking as a front plane, and just by clicking on the left button we will go to the sketch, then it will come on the front of your this screen, that in which plane you want to draw or make a model of your required design. So now we will design on a cell of a pressure vessels. So at first we have take the front plane, then go, suppose this is a cylindrical pressure vessels, then obviously I will make a circle. Suppose I can say this is 100 mm, and suppose the thickness of the cell is 5 mm. Then we have to create another circle. So this is, we can take 90. Not 90, not 95, I think. Then obviously the thickness of the cell will be 5 mm. Just I have thought. Then you just leave the sketch, or you can also extrude awkwardly, but I will go to the sketch, leave the sketch, and will go to the extrude boss. Okay, now suppose the whole length of the cell 1000 mm. So now we have created a cell that's thickness is 5 mm, outer diameter is 200 mm, means I have taken the 100 mm radius, so 200, and also the similar the inner diameter is 190 mm. Now the thing is that we have to create a hole on the surface of this cylinder for passing the fluids or any gases, whatever you are thinking. So then we can take a plane so that we can create a hole on the surface of the cylinder. So now the question is that which plane we will take. So obviously this is the front view and this is the top view, so we can take a top plane. Now this is the top plane, but we cannot design in this plane. We have to take a reference plane on the surface or the above the surface so that we can extrude it or extrude cut it. Then we'll go to the features. Then take a reference geometry. We can select as a reference plane. Yes, see, this reference plane is showing that 10 mm above the top plane. Okay, so you know this is the distance between the center to the upper means the outer cell diameter. It was 200 mm. So then we can take more than 200 mm. Suppose we can take 250, I think. Look, now we have created a reference plane which is 250 mm apart than the top plane of the cell. We can reduce this distance. We can take, this is the 200, 150. Let's see what happens. So this is quite general, that the radius was 100 mm. We have taken extra 50 mm apart than the upper surface of the cell. Okay, it's okay. Now in this top plane, we will draw the required geometry for the hole or the inlet of your required fluids. So then take this top plane and go to the normal to for design purpose. Let's go to the, suppose the inlet will be circular sections. Then we have to take a circles. This is a main, means mid of the reference, mid of this line. So we can take along the mid of this line. Suppose we want to create the inlet here. Suppose the inlet is 30, we can take 30 mm or 25 mm. Okay. So we have created 225 mm radius circular hole. Then we can give the dimensions, proper dimension for locating this inlet. Okay, the dia is 50, it's okay. Also this diameter, okay. Now the distance, you can take the reference distance from the outer side of this cell to the required position of your inlet holes. Suppose we can say this is 1000 mm long, so we can say that from the edge it can be 200 mm apart. 200, yeah. Also you can modify that is 200 mm. So you have created two circular sections from the 200 mm apart from the edge of these cells or the cylinder. Okay. Now left the cage and go to the features and extrude the boss. Here show select a plane or the plane face edge or which to the sketch features cross section or an existing sketch. So we have not selected the sketch, that's why it's showing. So at first we have to select the sketch. Sketch 2 we have taken, then we can extrude it. Let's see. See the direction is different. So we can change the directions. Now it is 1000 mm. So we can take as a, this is 50 mm apart, we can take as a 50 and 5. We can take as a 55 mm. Let's see. See, this is the just inner portion of this, the cells. Okay. Now this is a solid section, this is not the hollow, so that we cannot say that this is the inlet of your fluids or gas. So you have to create the hollow sections according to your required couplings. Means you have to proper make the joining of these inlets with the another mechanical fastener. So just I am not going to that mechanical fastener, just I am going that how will you create a hole to the for passing the any fluids or gas to the cell. So take this surface and go to the sketch. You take this as the 25 mm radius. We can take this is the thickness of this of these parts. We can take the 2.5 mm. Then we can take the radius as 25 2.5 2.55 means radius we can take 10 20 11.5. We can not 11.5, this is 22.5. We can take, let's see. Then go to the features and extrude cut it. You can increase the extrude cut section. You can say it is 65. If you want to give the 55, then it will be just up to the surface, and if you increase, then it may be just I have increased the 10 mm, that's why this portion is showing. can tell as a 55 mm. See, up to the surface. So I can just small increase this 57. Small increment. Okay. See, this is hollow. This is the inlet portion of your shell. Okay, you can also design or make a part to just the other mechanical parts for closing this inlet or something other else, but I am not going to that. I am just showing about the cell surface geometry. Similarly, you also create this similar drawing to these portions for outlet. Go to the here you see it's not aligned, means I have not taken the proper uh, center of this the previous this circle and this circle, that's why this has been created. So we can go back here, we can oh no. Here now this is concentric. Then go to the features, then extrude cut. This is also 50 7 mm. I have taken the 2 mm more than the inner surface of the cells. Okay, see. So one inlet and one outlet has been created on the surface of the cell. Now we have to, in the previous class I have already shown that how the tube sheets are generally assembled in these portions, isn't it? So
Yes, sir.
you can assemble the tube sheets as well as the pipes and the baffles. You can insert it inside these cells. Now the another portion is that the outer sections of this cell. Now I am going to the next part to assemble the outer section of these cells, the edge portion of these cells or pressure vessels. So the pressure vessels, the edge section of these pressure vessels, this will be a cylindrical or the required design, whatever you like, you can choose according to your desire, that in which way you will just cover it, the edge of these cells. So then we can go to the another part. So for making the outer parts of this edge, we have to create a just means sphere-like structure. So that's why you need to revolve any portion so that you can get the proper outer edge of the cell. So for doing that, at first we have to take a reference line. We can take a center line for revolve any sections. So you take a spy line from any portions. Suppose here I am taking a spy line. Then take a general line. Also you can give the dimension that what's the distance between these the these portion to these portions, or the total length. Suppose here to here, this is we have taken 200 mm dia of the cell. So this maybe you can take in, that is 39, you can take as a 100 mm. As well as the distance also you can take that these and these are, you can modify, you can take as a 35 or something, whatever you need. Now go to the another comments. Just you have to offset these sections according to a required thickness. Already it's showing 10 mm because I have given the 10 mm offsets. You can also increase that. Also make a closed loop for revolve. Okay, here this portion is open. You just click on the left button and just move it. To get this in a center line. Oh, it's already spoken, something is problem. Now I think both the points are in center line. Then you closed it. See, from my geometry, you are seeing that it's not proper design. But yet I am just showing that according to your diameter or the shape of the just revolve portion, you can change it. So then we can leave the sketch and we can go to the revolve boss. That it's showing axis of the revolution, in which axis we have to revolve that. So we can take this. Now so you can take the tubes, means gasket or tube sheet in these portions, isn't it? And this portion is only for joining with the nuts and bolts. Similarly, you have to create these portions to your shell whenever you will join with the tube sheets with the connected pipes. That's I have taken in the previous class. Okay. So now this is the head portion of this shell. Now we have to just create a hollow section for joining joining with nuts and bolts. Then what will you do? You can change the shape according to your desired spline. Okay. You can also change this the thickness for joining this with the bolts or nuts. So let's take this plane. We can go to the sketch. We can take a circle. We can take 175 mm. Now this circle we have created only for construction. Then you can make a hole according to your bolt size, bolt nominal diameter. So suppose here you can take the radius is 5 mm and the total nominal diameter is mainly 10 mm bolts you can use for join. Now here suppose 20 bolts may be required to join with this the head portion with the cells. So you don't need to draw these 20 holes. You can draw a single hole and then go to the commands linear sketch pattern, and there is one also circular sketch pattern. You take the circular sketch pattern and you increase. Here 4 is written, that's why it's showing 4 holes, 4 circles. You can increase that according to your required design. We have taken 6, 7, 8, 9, suppose 10. Okay. Then leave the sketch and go to extrude cut. See, it's showing up to the surface 10 mm. Or we can blind not to through both blind vertex. You can change offset from the surface up to the body, mid plane up to the next, through all blind we can take. See, hole has been created. Now you can, during assembly, you can insert the required bolt as well as nut for joining this portion with the cell of the cell portion of your heat exchanger, isn't it? So why have had I given to the assignment on the nut, bolt and flange? Due to this reason, so that you can just assemble, it can be easier to you for assembling this head part with the cell as well as any other parts on the just inlet of the cells, etc. Did you get it?
Yes, sir.
So is there any problem? I think I have shown each and everything, this head portion, cell portion, and also the tube sheet with the baffles, isn't it? Then what's the required portion has left? I think nothing. So for your design purpose, you can show the separate parts whenever you will just show your on calculations, and at the last you can assemble it just for demonstrations. You can change
So
the
this has
spy
to be
line,
connected to the flange.
not the flange means what can I say? Here you see, whenever the tube sheet will be inserted in this portion, then the outer diameter or the any outer portion of the sheets, suppose here just I am just giving an example. Suppose I can take the front plane, go to the sketch. Did you get it? Okay, for the simplify, I can also go to the sketch, to go to the Now see, this is the outer portion of the cells. You can insert the bolts with this section to the head of this cell, these portions. You can assemble it by using the bolt and nuts, isn't it? And in between this head and this cell, you can use the gasket, a small gasket according to the inner diameter of these cells, isn't it?
Yes,
Did you
sir.
get it? How will you assemble this?
Yes, sir. So that we
You
know
can
how to assemble. Sir, but about gasket, sir, how to place gasket there in between?
nothing, just a similar way. In the mechanical way, you just can take this the solid. You take this front plane. Oh, sorry. This plane. You go to the sketch. You take this the inner diameter of these cells. This will be only just for suppose 95 mm. Okay, you just only extrude this. Suppose this is 2 mm or 3 mm something. If this is 10 mm, you can take 2 mm. This will be closed like this, and these portions will come. This is what I have given. You have to insert that. Okay. But I think for this section, whenever you will use this, the head uh, of this cell, then you don't need these sections. You can also use the gasket for these sections also, as very small, very very thin. Suppose in between this the inner and this between this bolt, you can use that. But for your design purpose, I don't think you don't need. You can just only by using mechanical fasteners, by using a nut and bolt, you assemble it with this the head portion to the cell portion. Okay. You don't need any tubes, means gasket or any other things for
Okay, sir.
this purpose. But how will you design? I don't know actually. The tubes and other things, and what will be your inlet, what will be your outlet, that will be determined by your required design. Just I have here shown you that how will you create the inlet, outlet, and as well as the tube seats or the outer or head of these uh, cells. How will you create? Just I have helped you. What else? Is there any left?
Nothing, sir.
So Mondal sir,
Yes.
I think most of the sections I have shown here, the head part, cell part, as well as in the
Yes.
previous class I have shown
So
the
let us hear from the students if they have any specific queries.
I think they have not designed it. That's why they are not saying anything. And this is very, means you have to practice it. Otherwise, you can't access it so easily. Whenever you will create a new plane, you will face some problem. No,
Yes.
you will not
So
able to make a plane very easily. That's why I am saying that have you tried or not? And you
yes,
have
so
to.
has any one of you tried while Dr. Nitai was explaining this, illustrating these problems to you, and did you face any problem at this point?
Yes,
I
yes,
mean, I
sir.
must emphasize that this is the last possible opportunity to get a physical interaction on these issues or problem related to this assignment. Because in the next class, we will be starting, or you are supposed to work on the heat exchanger network problem. So if there are any issues related to the design or the drawing of these components in the SolidWorks, please get it clarified now.
So sir, like there is no need to draw the gasket.
No, I don't think, but it will depend. What will be the edge sections of your cell? Suppose just you want to just block the any other side of your cells, then you can use the gaskets. Otherwise, you have already by using, suppose here I have shown that this is already blocked. Okay, but these portions you can use by a small very thin gasket, but not this section. The thickness will be between this the outer diameter of this hole and the inner of this means this hollow sections. In this portion you can use a very less thickness means gaskets, but I don't think for just this purpose you have to incorporate that. You just simply make a bolt and nut and you assemble it properly for learning purpose.
Yes sir.
Otherwise it will be difficult to assemble that. Now you can assemble it very easily, this portion as well as the these portions, the edge of the cell.
Yes sir.
You
Yes
just
sir.
insert the bolt.
We have to just click the mate and select the
Yeah,
surface.
you can take only the four nuts and bolts, not need 10. If you want, you can increase that. But I am just telling. You just demonstrate it. That's I have created in this way. As well as you can also just insert another portions of the inlet of these cells, by giving some other geometry, etc. But that is also extra works. You don't need that. That's why I have shown here only simple circular inlet. If you want, you can also do that, but I will recommend simply you just show the circular inlet, and as well as you can join this bone nut and bolts with the edge portion of these cells with the head of these pressure vessels. And in the previous class I have shown that how will you design the tube seats and also the baffles and how will you arrange the tubes. You just simply open that and you just insert or assemble with the head sections. You just mechanically insert these bolts and screw it with nuts. হ্যাঁ স্যার যাব। So I am telling you again, if you don't practice, it's not so easy, because uh, mechanically modeling a heat exchanger, it's really a difficult job. It looks so easy whenever anyone make a model, but whenever you will try, then you will face some problem. But I will suggest you, if your is design parameters are right, then it will not be issue. Means dimension will be perfect. If anything wrong in dimension, then you will be in great trouble. You have to means think in the previously, that's when before going to the modeling, that what will be your the diameter, the nominal diameter of the bolt, nut, etc. Then what will be the flange thickness, then what will be the inner and outer radius of the cell, and how will you join them, as well as required tube diameter, tube thickness, cell thickness, and the outer portion of the head thickness, each and everything you have to calculate previously. Otherwise you will make a part model, but whenever you will be going to assemble it, then it will not perfectly work.
Okay, so I hope all of you, understand the, concerns from Dr. Nitai, and and you must have realized by now that unless you do it yourself, this is not going to happen. You will simply follow the steps, but you will not able to understand or reproduce them in your own way. So, any other clarifications? If not, then I think there are not much to discuss for today.
Excuse me, sir.
Yes, Adrija.
Sir, there's a request. Can the deadline be extended a bit?
No.
Because most of us are yet to complete with the mechanical design part and also.
So you have one more week, no? So generally, I think they almost by today is the 4th class or the 4th week. So you have one more week. Utilize your time completely, and then you submit it. And this is, as I said in the last class also, this is supposed to be a group work, right? So you have to coordinate among your group members and learn each other or help each other mutually. So that spirit has to evolve, right, in the group. And with that mindset only, the problems are designed, the timelines are fixed, and the group activity is proposed, right? So that is very essential or key. And if you are able to do that, then the timeline is absolutely fine and should be fine with everyone. I mean, this is from experience I'm telling you.
Okay, sir. Yes.
So any specific, Adrija, any specific problem that you are struggling with the problem, or something which, I mean, what is the reason for the delay that you, I mean, technically?
Sir, actually, my teammates lost like a lot of time in doing the iterations and all. So finally we are done with the design part, but the mechanical design we have not yet started. So, and also actually the next week we have the test week, so that's why I was thinking. But okay,
that's a different issue. See, the mechanical component design is not very tedious. I mean, the process design is quite actually extended with all the iterations and all, but mechanical designs is quite straightforward. Possibly you might need to spend some effort with the SolidWorks drawing, but that you have to do.
Yes, sir. Okay, sir.
Okay, thank you.
Thank you, sir.
So this is, I just wanted to make this message clear to everyone that, extending the deadline is not always the solutions, isn't it? Because you see that you will be having something or the other coming up along the way, isn't it? And also if you try to manage the work throughout the duration of the course, you will not have this last minute rush ups, right? And also the second problem is coming along the way, as you might have realized today from the lecture of Professor Ganguly, that the second problem is already in the way. So you also need to keep your energy and focus on the second problem starting from the next week. So you will be also engaged with that. So please do not misunderstand or get it wrong that we are against, this helping you in extending the deadline. Possibly that is not the way to actually make a benefit out of this course, that you may feel that you can do better with the time, with the extended timeline, but then you can also do the same thing meeting with the timeline. Trust me on that.
Yes, sir. We understand.
Anything else, Snehbandhu?
Sir, sir, just wanted to ask about the support.
Yeah,
Like,
I think a support we can skip for the heat exchanger. No need of support design, because you have done extended support designs already in your previous semester for the pressure vessels design. So here we can skip the support designs.
No, they have not done the saddle support. The heat exchangers are typically placed on saddle
Yes.
support. So they have not done the saddle support.
So what
If
do you suggest? Shall we include
that
that
is
support here or for the evaporator? If you are at all planning for the evaporator.
saddle support, we can have a quick saddle support. I think I have shown you the pictures and the elements of saddle support, but when it comes to finding those that angle and those dimensions, if you're submitting it next week, how is it possible?
So last week
We'll see to it later. I think we'll see to it later, because I can give you some. Your IS code does not have anything on the saddle support, right, for the heat exchanger?
Possibly not. I can have a look once more.
No, students?
They must be knowing better than
no,
me now.
Snowbandhu, is there? No, right?
no, sir.
Okay.
Just what is the problem? What, where is it? Where is the problem, Dr. Ganguly?
No. Problem is that whether they should do support or not. They should do the support of the heat exchanger. They should do any design or not.
Now, tell me one thing. I think the first design course which they had, in that was supposed to do support, isn't it? The first design before this, the design course that was there.
They have learned the elements of saddle support, but detailed design they have done with the skirt support, because that is not a full-fledged design course. That half goes to the fluid flow lab and half is the design. So they know how saddle support, what is the saddle support, why saddle support is required for heat exchanger, and what are the elements of it, what angle is involved. So they are aware of it. But whether they should do it for this particular problem, we can revisit this later. For the time being, let us you can go ahead and submit it without the support.
Yeah, at least
What do
the
you say?
heat exchanger details they have done properly. That's.
What do you say? What did you say? I didn't get it.
The heat exchanger details, if they have done properly, they know all the tube details, the shell details, etc. Support, I believe, is common for any pressure vessel. It can be
any pressure vessel.
Exactly, that was the point. Yeah.
Right.
It is not specific to heat exchanger.
Not specific to heat exchanger.
But
Exactly.
I believe they know it already, and it should not be difficult. See, the only thing they need is the total weight of the heat exchanger. Based on that, they are supposed to do the design, isn't it?
They know where to look for it and all those. So that is there. They know where to look for it if it is required. Yes.
See, it is not IS code. I believe that Professor B.C. Bhattacharya's book.
Okay, it has all the details. Yes.
So they know about it. It's nothing new.
Yeah, leave saddle support. Yes.
Okay, so any other concerns from the students?
Excuse me, sir.
Yes.
Sir, I've done the design part, and then in the first iteration, I got RE tube side is around 5K, 15K, and RE shell side is also about 10K. But when I did the iterations, like the Reynolds number in both the cases are constantly decreasing. Like when I got the relative error in the range, like below 5%, the RE shell and RE tube went on to 5K is tube and then 7K is shell. So will that be fine, or do we have to do some like
No,
take
I
other?
think since it is more than 1,000, ideally it should be more than 10,000. But since you managed to get more than 5,000, let us go ahead.
Okay, sir. Okay, sir. Thank you, sir.
Okay then, so if there are no more questions or clarifications from any one of you, I think let us close today's class. And if you have any queries, feel free to post in the Teams. We will try to respond to them as and when we receive them. And let us try to to stick to the timeline for the next week as the submission date for this problem. Okay, with everyone.
Okay, sir.
So then, thank you all. Thank you. See you all next week.
Thank you, sir.
Thank you, sir.